speaker again, and
yeah,
15 minutes, I think, right?
12 right now, yeah.
12. Okay. It's a problem with sound, isn't it?
Yes, yes. Daniel?
Not really, very, very faintly.
What about now?
Yeah, now it's better.
Yeah.
Okay, let me see, then I just put it up. Here we go. Okay, so now it's better? Okay, perfect.
Yes.
Good. So I thank the organizers again, and so it's a great pleasure to give these lectures, and also it's I was very happy by listening to Henri's talk, because willingly or not, I mean, this fit very, very well together. And so in particular, I mean, Henri mentioned these two applications of Kähler-Einstein metrics, namely uniformization results and the stability of tangent bundles, which seem to be of a quite different flavor. So more or less the mantra of my lectures will be that they're not as different as you might think if you take a slightly more algebraic point of view. And also I can actually pick up on this last discussion, which was so regarding the question to Henri, what's the difference, or what do you get if the tangent bundle of a Fano manifold is stable? Well, the answer is you get this Hermite-Einstein metric, and that's a priori much less than having a Kähler-Einstein, so Riemannian metric, which gives you much more information like geodesics and so on. But also, again, the message from my talks will be that sometimes, or very often, stability of the tangent sheaf or bundle is enough to have give very strong information on the geometry if combined with other methods. Yeah? And so the aim is to explain one prototypical theorem, which also works on singular spaces where the sheaf theoretic results, which I'm going to use, are somehow much easier generalized to than the Riemannian or Kähler geometry methods that Henri was talking about, although there has been a lot of progress in this Kähler metric business on singular spaces in the last, let's say, 10 years. Okay, so the final goal, say, will be to discuss the proof of the following prototypical result, which is a uniformization result for singular Fanos. And so this is not the most general thing we can prove, but so this, I hope, conveys the main ideas and just gets rid of some technical problems that you encounter and which are actually difficult and not so easy to deal with when you want to prove the most general result. So the theorem is that you look at the terminal Q Fano variety. I will explain what that means, such that the canonical extension, so this is an extension EX, which is built from the tangent sheaf and the structure sheaf, and you assume that that's semi-stable with respect to minus Kx. If this equality here holds, which should be familiar after Henri's talk, then X is actually Pn modulo a finite group, where the group acts on Pn by projective linear transformation, and the action is free, actually not just in codimension 1, but in codimension 2 in the terminal case. So there is a codimension 3 subset of Pn, where this, if you take that out, the action of the group is actually a free action. The quotient is nice. Yeah, so that's a uniformization result. It works for singular Fanos, and it involves a lot of terminology, and I'm going to explain all of this terminology. I'm going to explain terminal singularities. I'm going to explain about the canonical extension. I'm going to spend a lot of time, especially in this first lecture, to talk about semi-stability from a sheaf theoretic point of view. And mainly the point is to show and to discuss the semi-stability not just of bundles, but also of sheaves, and point out a little bit the small tricks you have to use in order to make sense of the singularities of the sheaves. And sometimes they also they live on singular spaces, so you have to think a little bit. And so that's why I'm going to spend some time. Yeah. So the topics are listed here. So roughly the first bullet point is what I'm going to talk about today, semi-stability and Chern classes on normal varieties and for sheaves, in order to explain the sort of toolbox, which is different from the scalar geometry toolbox, in that it just looks at sheaves and bundles and this stability. Then in the second lecture, I'm going to talk about terminal singularities and flatness criteria on singular spaces. So these are flatness criteria for certain sheaves, and they will appear in the first lecture today in the case of bundles on smooth manifolds. And then finally, in the last lecture, I will talk about what this canonical extension is, where it comes from, why it's interesting. You see it's related to Tx, so stability of this canonical extension is related to the stability of Tx. And I will prove the theorem, and then depending on the time, I will discuss some ramification of this theorem, some examples, some more explicit stuff. Yeah, so that's the plan. Okay, so the second paragraph or second chapter is sheaf theory. And so the idea is that we have to deal with singularities of sheaves, and they tell us something about the singularities of the space that we're looking at. And so I'm just going to run, not too fast, through the notions that were developed in order to deal with singularities of sheaves, and they look at, they come from commutative algebra mostly. So X, if not stated otherwise, will always be a normal variety. And then we look at coherent sheaves. Okay, everyone I think knows what that is. It's a sheaf, it's not locally free, so it's not necessarily locally a direct sum of O, but it's the co-kernel of a morphism alpha from locally free sheaves. And then if, okay, the most nice coherent sheaves are the locally free ones corresponding to holomorphic vector bundles, but that's not always what we have in geometric applications. But some sort of regularity will be present, and that's related to torsion and to reflexivity. So a coherent sheaf, F, is called torsion-free if every stalk of the sheaf is a torsion-free module. So what does it mean? So it has the following property, which is obvious for vector bundles. So if you take sigma, an element in the local section in your sheaf, and you multiply it with a holomorphic regular function defined near that point, and you get 0, then either the function or the section is 0. Yeah? So that's more or less obvious for locally free sheaves. And that's a property, if I impose that, that will somehow exclude the worst pathologies, which I don't want to see in geometry. Okay, so what what implication does this have? So if a sheaf is torsion-free, yeah, then I can look at this natural map. I can dualize. So upper star means dual. So I take the Hom sheaf of F into the structure sheaf OX, and I do this twice. So I do Hom of F into OX, and then I have a natural map from F into the double dual. Yeah, and if it's torsion-free, that's injective. Yeah, so actually the torsion elements in this sheaf F are exactly, that's exactly the kernel of this delta, this F, from F to F double dual. Yeah. So, okay, if you have this injective map, then you can ask whether it's surjective. In general, that's not the case. And so you make this a definition, and you call a sheaf F reflexive if this map delta is is an isomorphism. Yeah, it's injective and surjective. And in case of torsion-free sheaves, this just is a question about surjectivity. Yeah. Okay, so that's a purely, say, module theoretic commutative algebra definition. So what does it mean? It's actually tied very closely to geometry, and these two conditions are very well suited to geometric considerations, which is why I'm going to impose them. Yeah, so first, torsion-free, what does this mean? This means that if I have a non-zero section in my sheaf, it cannot be generically zero. Yeah, so I can look at the, okay, I look at an open set, I look at a section, and then if this section is zero on some on some open set of my open set subset, then it's actually zero. Yeah, so I don't have these sections which have support on a subvariety. So that's somehow, I think, a geometrically meaningful condition. And the second point, too, this lemma explains the meaning of reflexivity. Yeah, so if I already have a torsion-free sheaf, so one which does not have sections which are generically zero, but which are non-zero, then it is reflexive if the following extension property holds. Yeah, if I take any open set U, it's down here, in X, and I take another a closed set A inside U of codimension at least 2, yeah, so like a point in a surface or a curve in a threefold or something like that, then the restriction map, which I have from sections on the bigger open set U to U minus A, is surjective. So this means that sections in F automatically extend over codimension 2 subsets, like A. Yeah, so this, if you come from a holomorphic or function theoretic background, this means the Riemann extension theorem, the second, holds for F. Yeah, and that's a very geometric condition as well. So it's an extension requirement on sections, which means that there are no sort of singularities in this sheaf which lie in codimension 2 or higher in some sense. Okay, so that's the meaning of torsion freeness and reflexivity. And why am I dealing with these? You will see, and not just with vector bundles, you will see if I go to the examples. So not the first three, but later, the examples on the right-hand side of the page, which you can't see yet. So let's look at a few examples. So locally free sheaves are perfect. They are torsion-free and reflexive. What is very nice is that if you have a torsion-free sheaf and you have a subsheaf, then it's automatically torsion-free. For example, you take a locally free sheaf E, and you take some subvariety Z in your X, and then you look at the sheaf of sections of E that vanish on Z. That's a subsheaf of E, and that's torsion-free. The image of this this sheaf inside E is torsion-free. But these sheaves are not necessarily reflexive. If E and Z are as above, then if my codimension of the subvariety Z is bigger than or equal to 2, then this is not reflexive due to the following lemma. So this lemma says that if I know a reflexive sheaf outside of some codimension 2 subset, I know it everywhere. So it states, the lemma states, if F and G are reflexive on my normal space X, and my subvariety has codimension at least 2, and I know that F restricted to this complement. Okay, maybe I draw a picture. Let me do that. Yeah, so the statement of the lemma is I have my X I have my closed set Z, the codimension of Z in X is bigger than or equal to 2. And then I have two sheaves, F and G, that are reflexive and that are isomorphic on the complement of Z. So F isomorphic to X minus Z minus Z. Then F is already isomorphic to G. Yeah, and that means, okay, it's not so surprising because reflexivity by the previous result has something to do with extension of sections. And in fact, what you do here is you look at the Hom sheaf, let's say of F into G. That's also reflexive because G is reflexive, and that means that you can extend homomorphisms, in particular these isomorphisms on big open sets to the whole variety. Yeah? So that's also that's a property which is also very useful for say birational geometry and for geometric considerations. Okay. Okay, so you should see my my slides now again. Okay, so that that means that reflexive sheaves have these useful properties of having that they are sort of determined by the restriction to a big open set. Yeah, and so what is our main source of examples? Yeah, so that's the following. You take a locally free sheaf on the smooth part of X. Yeah, so you have your normal variety. It has a smooth part, a regular part. Since the variety is assumed to be normal, the complement of this smooth locus has codimension at least 2 in X. And now you look at the inclusion I from the regular locus into X, and then you take your locally free sheaf, E, on the regular locus, and you just push it forward to X. And that's a reflexive sheaf on X. And that's, as I said, the main source of examples, and that's the main reason why I look at reflexive sheaves, is because from a geometric point of view, many sheaves rise in this way. Yeah, for example, the following. Yeah, so you can look at the tangent sheaf. Yeah, you have your singular, potentially singular normal variety X, and okay, you struggle to imagine what the tangent is. The tangent sheaf should be geometrically. Okay, there is some commutative algebra definition maybe in terms of derivations, but you have much more idea and much more intuition about the restriction of about the tangent bundle, in this case of the regular locus. Yeah, you can look at the regular locus, you look at Tx rec, that's the tangent bundle, the holomorphic tangent bundle. It has to do with derivations, it has to do with derivatives along curves, and so on and so on. It might carry a Riemannian metric, a Kähler metric, and so on. So that's a thing we understand very well. And now you just push it forward to X. Yeah, and then you get Tx, which is the tangent sheaf, and it's a reflexive sheaf. Okay, and similarly, you can look at forms, so holomorphic P forms or regular P forms. You look at the regular locus X rec, you look at the sheaf of holomorphic P forms, omega P X rec, and you push it forward to X, and you get what I denote by omega X bracket P. And one special case of this second construction is small omega X, which is just the special case P equal the dimension. So you look at the bundle of holomorphic N forms on the regular locus, and you push it forward to X, and you get a reflexive sheaf, and the rank is 1 because you're pushing forward a line bundle. And so these are geometrically meaningful examples, and these are the things we're going to deal with, and that's why I want to consider reflexive sheaves. Or I have to consider reflexive sheaves once I leave the world of smooth manifolds and I deal with normal algebraic varieties. And so the rank 1 case is special in the following sense. So if I look at this proposition, if F is a reflexive sheaf which has rank 1, so it's generically it's a line bundle, then on a manifold, so on the regular locus, this is automatically locally free. Yeah, so reflexive of rank 1 on a smooth space is automatically locally free. Yeah, and then what about the whole space if my X is normal? Yeah, so since my F is reflexive, I know it's determined by its restriction to a big open set, so like XREG. Yeah, so then I can, and so I know that if I have F reflexive on X, the restriction to the regular locus is locally free, then I can push forward again. I do this I lower star F restricted to XREG, and I get another reflexive sheaf. Well, but these two reflexive sheaves, they agree on the smooth part, so they have this, which has codimension 2 complement, so they have to be the same sheaf. Yeah, so this means I can understand this F by restricting it to the smooth part. There it's a line bundle, and then I can push forward again. And globally, this F, this reflexive sheaf of rank 1, is nothing but a sheaf of the form OX of D for some Weyl divisor D on X. And we all know from Hartshorne that not every Weyl divisor D on a normal space is locally free, so it's not not necessarily Cartier, which means that F is not necessarily locally free, and the correct sort of sheaf theoretic extension, which corresponds to going from Cartier to Weyl divisors, is going from locally free sheaves to reflexive sheaves of rank 1. So this is, so now we understand how reflexive sheaves of rank 1 on our normal space X look like. They're just of the form OX of D. Okay, great. So what can I do with a reflexive sheaf of rank 1? You see, if you look at the bottom of the page, this is moving towards the definition of stability that already appeared in Henri's talk. Okay, so this is just noting the following. If my X is a normal projective variety, and I have an ample divisor, and D is a Weyl divisor on my X. So, for example, a D arising via this observation, which I just noted, namely the D coming from a reflexive sheaf of rank 1, then I can define what it means to intersect this Weyl divisor D with h to the n-1. And the picture tells you how to do that without proving that this is sort of well-defined and independent of all the choices made. Yeah, so what can I do? My H is an ample divisor, so some multiple of it is very ample, so it has many sections, and so I can take n-1 elements in this multiple of H and intersect them, and I get a curve. Since H is the multiple of H is very ample, this curve can be varied a lot. In particular, I can avoid the singular locus of X. Yeah, the singular locus of X has codimension 2, and I can choose my elements, my n-1 elements in H, such that the intersection lies completely in the smooth locus of X. And so now I have this Weyl divisor D, And I know that OX of D is a reflexive sheaf which on the smooth locus is locally free. So I can take this locally free, so this line bundle OX of D, and I restrict it to the smooth curve lying in the smooth locus. And that's a line bundle on the curve, and I can take the degree on this curve. And then I get a number which I have to divide by m to the n minus 1 if I had to take the multiple m of h in order to have these all these sections that I use to produce C. Yeah, so if that's this number d times h to the n minus 1 is exactly this degree written here if h is already very ample or say semi-ample or something. Okay, so that is just an observation that you can define an intersection number between a Weyl divisor and h to the n minus 1 on this normal space.
Excuse me, you probably also want this curve to be smooth, right?
Yes, yes. So this will be smooth by Bertini theorem. Okay, I take a general an intersection of n minus 1 elements in some multiple of h. Exactly. And then, of course, I mean, this is not, it's not obvious that this is well defined, that it doesn't depend on the multiple, that it doesn't depend on the chosen curve. But okay, you can prove that. I just wanted to point out that somehow that's a geometric, I wanted just to explain the geometric idea of why this is still possible to define this intersection number, and because essentially you're avoiding the singularities both of the reflexive sheaf OX of D and the singularities of the space X. Yeah? And so once you have this, you can intersect a Weyl divisor with h to the n minus 1. So you can define the intersection of C1 of F with h to the n minus 1 for every, say, torsion-free sheaf. Yeah? So I have this normal projective variety X, and I have a torsion-free sheaf F on it. Then I can do the following. I can take the wedge power, the maximal wedge power. So this torsion-free sheaf, because it's torsion-free, it has some generic rank. So this means that outside of some closed subset of X, it's a vector bundle of some rank. And then I take the top wedge power, that's another sheaf, and then I take the double dual. So why do I take the double dual? The double dual of a sheaf is always reflexive. So at least in our situation here. So this means that what I have here is a reflexive sheaf, and what's the rank? Because it's the maximal wedge power, it's reflexive of rank 1. Yeah, and so this means it's of the form OX of D. And so I can do the following. Whenever I have an ample divisor H on X, I can define the intersection number C1 of F dot H to the n minus 1. And on the left-hand side, that's just a notation. This will be a number, and it's the number D times H to the n minus 1, where I explained how to compute this D times H to the n minus 1 above. So this means I have a way of intersecting, say, the determinant of F with the n minus first power of an ample bundle H, even on a normal variety. Okay, and so with this number at hand, I can now define what the slope is and what semi-stability is, which already appeared in Henri's talk. Yeah, so if I have a normal projective variety, I have a torsion-free sheaf on X, I fix an ample divisor H, I call this number mu H of F, which already appeared, as I said in Henri's talk, which is C1 of F times H to the n minus 1, which I just defined down here on the left-hand side, divided by the rank, the slope of F with respect to this H. Yeah, so this depends on H. If I change my ample line bundle H, this number will change usually. And so that's why I sometimes write mu H of F. If H is clear, I sometimes will just write mu of F, and I call this the slope. Yeah, and then semi-stability is a condition on F, which can be explained or can be defined in terms of these slopes as follows. We call our torsion-free sheaf F semi-stable if for all coherent subsheaves, so all sub-objects G in F, which have not the same rank as F and not zero, the rank is not zero, we have that the slope of this sub-object is less than or equal to the slope of F. Yeah, so semi-stability would allow less than or equal, whereas stability would require strict inequality. So while one can certainly just define this, let's think a little bit about what this means. And we will see that the intuition I'm trying to convey now is correct in the examples which I'm going to exhibit soon. So what does this mean? So this slope is some sort of weighted positivity of my sheaf F. So it's weighted by the rank. Yeah, it's some degree divided by the rank. And so being semi-stable means that there is no subsheaf G, which sort of contributes more to the overall positivity or this overall number mu of F as it should be according to its rank. Yeah, so this is some sort of balanced condition. Yeah, if you think in terms of curvatures as Henri defined it, you see that there are no directions in my F which are more positive than others and carry more of the positivity than they should be, that they should carry on average. Okay, so as I said, I will explain or give a few examples on the next slides. Just take a look at the following lemma, which I was, as you see, too lazy to copy here in my handwriting. This just gives some sort of properties which are rather formal of this notion. I will not explain these in detail. They just explain that you have some freedom in checking this stability. For example, number 1 says that stability, and all the statements also holds if you replace stability with semi-stability. So V is stable if and only if the required inequality holds for all subsheaves G, with the additional sort of regularity property that the quotient of, here it's V by W, up here it would be F by G, is torsion free. So that's a regularity condition on the inclusion of G in F. 2 says that stability is sort of invariant by twisting with some line bundle. So I can shift my sheaf by twisting it with a line bundle F, and then check stability, and that's equivalent to stability of V. Another property which is very important, especially if you think about these geometric setup, or these geometric examples of sheaves that I'm dealing with coming from geometry, like the tangent sheaf, these sheaves of differential forms. V is stable if and only if the double dual is stable. So that essentially allows us to work in many cases with reflexive sheaves. And then let's just look at the last thing. Stability can be checked on the dual as well. So V is stable if and only if the dual is stable. That's just, as I said, rather formal properties of this notion. Yeah? However, there is one thing which I will use at least implicitly, and which is very, very important in the also theoretical development of this theory of stability or semi-stability. That's the behavior under tensor products. Yeah, and the following is not trivial, and it's highly non-trivial. So I would say, so if you take E and F, two H semi-stable sheaves on my normal variety X, then, okay, first the tensor product E tensor F is not necessarily torsion free. So let me take the double dual, and then the statement is that that's semi-stable as well. So in some sense, you could say tensor products stay semi-stable. As you see in the formulation, that's not the full truth after taking double duals, but essentially that's lets you remember this statement. So stability or semi-stability is somehow preserved under tensor product. So why is this important for us? Well, let's look at the following example. So it's a meta example. So let X be a manifold.
Excuse me, and is
Yes.
this theorem proved by restricting to generic curve and using Merter-Romanatan criterion?
I think you can do that, yeah.
Okay.
But even there, on the curve, you have to prove this tensor product statement.
Yeah, separately.
And
Yeah.
also, is it true that if the two things are actually stable, then the product is polystable?
Yes.
It is true, right?
Yeah.
Okay.
But
Because
I'm not going.
buttons-
I'm not going to use that. I think. I mean, polystability will not appear too much in my lectures.
Okay.
Yeah. So I'm just trying to collect
All right.
a few things that are used in the following. Yeah, but that's right. There are more. So there is a circle of results here, and depending on, I mean, sometimes they're classical on curves. Then sometimes they're classical on higher dimensional manifolds. And then if you think about normal projective varieties, usually you have to think a little bit extra, but that's not usually that's not the point.
But they're all non-trivial. Non-obvious, all of them. So you just have to use them.
Yeah. And so I just want to point out why is this somehow interesting for us, or I mean, how will this appear or can this appear? Yeah. So already explained that using these analytic methods, you can show that many classes of projective manifolds have a tangent bundle which is semi-stable, either with respect to a specific ample divisor or with respect to all ample divisors, as in the KX trivial case. So then let's just apply what we just learned. So about these tools. So if Tx is semi-stable, then the dual is also semi-stable. And then I can tensor these two semi-stable, say, bundles or in sheaves and take the double dual, and that's also semi-stable by the theorem above. But what is this this tensor product and then taking double dual? That's just the endomorphism sheaf of Tx. Yeah? So this is how this might or will appear here. So it's already non-trivial to see that if Tx is semi-stable, this endomorphism sheaf of Tx is semi-stable. Okay, so let's just give a few non-geometric examples and then go to the geometry to get some feeling about this semi-stability. So let's do it on P1 first. Okay, we probably all of you know that every vector bundle over P1 splits as a sum of line bundles. And so if I take a rank 2 vector bundle, it's of the form O of A1 plus O of A2. And then if A1 is not A2, then E is not semi-stable. And if A1 is equal to A2, then E is semi-stable. Yeah, there are no stable bundles because of this splitting. Yeah. Okay. Yeah. So this is what I mean about this is what I meant about when I said this is a balanced condition. Yeah. If you look at this sum of two line bundles, then if A1 is not equal to A2, one of them is bigger, and then it would contribute more to the overall degree as the other one, and so as it should be, as it should contribute. So only if these two numbers are the same, I'm sort of balanced. Well, another thing which is which already indicates that stability, if you know that a bundle is semi-stable or stable, that this gives you some information about sections, and you can control sections, is the following. So B. So let's look at, again, a rank 2 vector bundle, but this time over Pn, not P1. And then I will normalize it in the following way. So I look at the first Chern class because of the topology of Pn. This is just a number. So this is a number, an integer. And then I take this k of E, which is either minus 1/2 of this C1 of E if this is even, or if C1 of E is odd, I add 1, and then I do minus C1 of E plus 1 divided by 2. Yeah, so what does this, how is this made? So this is made exactly so that the C1 of E twisted with K of E is either 0 or minus 1. Yeah, so this is a sort of normalization. Of course, I want to normalize to the case 0, but that's not always possible. So I, because of odd numbers, so I normalize this twist to either have first Chern class 0 or first Chern class minus 1. Okay, and then it's really an exercise, very short exercise, to show that E is stable. Note that here there is only one ample bundle, namely the hyperplane bundle. So E is stable with respect to H, or O of 1, if and only if this normalized sheaf has no sections. Yeah, so let's think about why this could be true. So assume, for example, that this normalized sheaf has 0 first Chern class, so 0 or minus 1, so 0, and then assume you have a section. Yeah? So a section is nothing but a homomorphism from OX into this normalized sheaf, and this will give you a degree 0 subsheaf of E, essentially. Yeah? And so then you cannot be stable because C1 of E is already 0. Yeah, so that's, as I said, it's a small exercise here to prove this equivalence. But it also, as I said, it shows you that stability, if applied correctly, and for example after this small normalization, tells you something about sections. Okay, let's move to geometry. It's not difficult, but maybe a little bit more than an exercise to show that TPN is stable. Okay, you know it because Henri told you that if you have a Kähler-Einstein metric as the Fubini-Studi metric, then the tangent bundle will be stable. Yeah, the same is true for varieties, other flag varieties. These are projective rational manifolds of the form G mod P. And say I choose a simple complex Lie group here, and P is a parabolic, then also that tangent bundle will be stable. In the search for other examples, we come to the world of Fano manifolds, which was already mentioned by Henri, and it also appeared in this discussion, which was happening at the end of Henri's talk, namely, what is the meaning of stability for the tangent bundle for Fano manifolds? Yeah, so we call that a Fano manifold is a projective manifold for which the anti-canonical divisor minus kx is ample. Then it's because of Kodaira vanishing, the Picard group is a discrete abelian group, and so it has a rank. This is the rank of the free part, which we call the Picard number. And so one interesting class of Fano manifolds is those where this Picard number is 1. For example, if I look at hypersurfaces, so if D is less than or equal to n, then a smooth hypersurface of degree D inside Pn is Fano with Picard number 1 as long as I think I don't have to restrict the dimension here. Yeah, so low degree hypersurfaces in Pn give examples of Fano manifolds with Picard number 1. And there is a very long-standing conjecture related to this discussion about stability properties of Fanos in relation to the existence question for Kähler-Einstein metrics. And this conjecture states that for every Fano of Picard number 1, Tx, that's a natural, in this case, vector bundle, is semi-stable with respect to the most natural and the only ample divisor you have here. This is minus kx. Yeah? So the Picard number is 1. So there is only actually one ample divisor, and it's a multiple of minus kx. And that's a very interesting conjecture because it was believed to be true by many people in this business for a long time. Yeah, and why was it believed? Because it's true for dimension less than or equal to 6. And it's true for complete intersections. And it's true if the Picard group is actually generated by minus kx. Yeah, so if the index, the so-called Fano index of x is 1. Yeah, so we know that the Picard number is 1. So pic x is z times some ample bundle or some ample divisor. Minus kx is an ample divisor. So it is inside of this line here. But so under the assumption that it actually is a generator, then this conjecture is also true. However, very recently, a counterexample was found by someone called Kanemitsu. So it's false in general. It's not true. So you see, it's a subtle issue. So the stability properties of Fano manifolds and even this stability of the tangent sheaf, tangent bundle, it's very subtle, and there are interesting geometric arguments in all of these proofs here, which I can recommend.
I'm sorry, can I ask something? So Picard number 1 is essential here. So if you blow up Pn at one point, it's probably obvious. Is it true that it's not stable anymore?
Obvious.
Can't think right away, but I mean, it fibers over Pn minus 1.
Yeah. So it fibers over. So the point is, I mean, there was a refined version of this conjecture where if the Picard number is 2 and higher, that somehow it, okay, in most cases should not be stable, and the destabilizing subsheaf should come from some sort of vibration or something.
Okay.
Yeah?
Okay.
Yeah. So, but now since this conjecture is no longer true, I don't know whether I should somehow propose these more general conjectures. Yeah.
Okay. Sure.
Yeah. Okay. So as you already saw from Henri's talk, So if I go to the other pure geometries, in high dimension, this means minus kx ample, so Fano, I discussed that, then kx trivial and kx ample. So if kx is trivial, then Tx is semi-stable with respect to any ample. This can be proven using the existence of a Kähler-Einstein metric, as Henri explained, or using Miyaoka's generic Neffness theorem. And so, okay, I gave a few examples here, right? So if I take a quartic in P3, a quintic in P5, or an abelian variety, the tangent bundle will be semi-stable. It's not necessarily stable, as you can see in the case of abelian varieties, where the tangent bundle is a direct sum of trivial line bundles. So it's just polystable and not stable. And that's the general statement. And Henri's theorem, the theorem he mentioned, the theorem of Lübke and Kobayashi, already tells you that the meaning that you expect to have the direct sums in the polystability decomposition to have some geometric meaning. Yeah, and then if you go to the other end, if kx is ample, then Tx is kx semi-stable, again, maybe by the existence of a Kähler-Einstein metric. Yeah. And so this was already mentioned, so I will come to it. So if I do higher dimensional geometry, sometimes things get complicated very, very quickly. And that's also true with respect to sheaf theoretic stability. And so I want to restrict my dimensions, so I want to cut down by hyperplane sections. And an extremely important tool in all of this is the Mehta-Ramanathan theorem, or in the version I write here for normal varieties, and there's even an effective statement due to Flanner. It says the following. So if I have a normal projective variety with an ample divisor, and I take an H semi-stable sheaf F, then there exists a natural number, a D, such that for every sufficiently general member, I should say it should read D times H, or the number should be M. Yeah, so I have to go to some multiple of H, but then for every sufficiently general member, say D, the restriction of my sheaf down to D is again semi-stable. Yeah, with respect to the polarization, the ample bundle that I get when I restrict the ample bundle to D. And so this is an extremely important tool that allows us to reduce dimensions from n. So if you look at it, in principle, down to 1. Yeah, you can apply this repeatedly. And so this then it says that if I take my normal projective variety X, which might have singularities, and I take an ample divisor, I can take a high enough multiple of my ample divisor and n minus 1 sufficiently general elements in this multiple. I intersect these divisors, I get a curve. This will avoid the singularities of X completely. The curve will be smooth. And then the restriction of my sheaf, which will be a vector bundle on this smooth curve lying in the smooth locus of X. So it seems as if my whole theory can be reduced to the curve case by this theorem. And that's almost true. But one really, really important information is really carried by surfaces, so complete intersection surfaces, S, instead of complete intersection curves. And this has to do with the fact that Lefschetz theorems, so about the fundamental group of my X, and the comparison with the fundamental group of a hyperplane section, or in other words, the second Chern class, I can only cut down to surfaces and not cut down to curves. Yeah, so let me explain that. And for that, I have to explain a little bit about how to attach a second Chern class to my bundles. So I think most of you will have seen that. So that's just to set the notation and to explain this to those students that have never seen this. So first of all, so the idea is I want to attach two, namely the first and the second Chern class topological invariants to my holomorphic bundle, which somehow tell me something about the topological type of my bundle, which means the underlying topological vector bundle. So for line bundles, this is easily explained. Yeah, if I have a holomorphic line bundle, then the isomorphism class is an element in H1O star. And then I look at the exponential sequence. 0 goes to Z, goes to O star, goes to 0. And then I get a connecting homomorphism in a long exact sequence from H1O star to H2 of X. And that's called, if I apply this to this isomorphism class of a line bundle, this is called C1 of L. And so if V is a vector bundle, the top exterior power is a line bundle, and I can apply this. Yeah, and this is compatible with the earlier notation where I intersected, I wrote down an expression of the form C1 of F intersected H to the n minus 1. Yeah, and so if my vector bundle is a direct sum of line bundles, then I can define higher Chern classes via the following formal equation. I just multiply 1 plus C1 of the line bundles, and then I order this according to degree, and this gives me Chern classes Cj in H2j x comma z. And so the so-called splitting principle tells me that this gives a definition not just for V, which are direct sums of line bundles, but for arbitrary V after doing some geometric construction. Yeah? And so what are the properties of these Chern classes? They are functorial. So if I pull back a vector bundle V and compute Cj, this is the same as pulling back the corresponding class. Moreover, the left-hand side, if I denote the left-hand side in the above expression, so if I take the product of these 1 plus C1 and I write this out in terms of degrees, and I sum this up, this is called the total Chern class. This is multiplicative if I have exact sequences of vector bundles. Yeah, I think this was mentioned already by Henri. Yeah, so just the message is C1 of a line bundle is clear, and it can be used to define higher Chern classes via this splitting principle, and they behave nicely in exact sequences. Yeah. So by this construction via direct sums of line bundles, formulas for these higher Chern classes can be derived from formulas for sums of line bundles. Yeah, so I just give a few examples. For example, the total Chern class of a dual of a vector bundle is the dual of the total Chern class, where what is the dual of a class? Well, it's written here. So alpha dual, if alpha is a sum of alpha j, it's just switching signs in odd. So in degrees 2 times an odd number, and keeping the sign in the case of 2 times an even number. Okay, so these are formulas. This is a formula derived from the definition. So if you play around with this a little bit, you come to computing the second Chern class of an endomorphism bundle, or in other words, V star tensor V, so C2 of end V, and you get the following formula. Yeah, so this is if you take a vector bundle V, you compute the second Chern class of end of V, then it's this. It's 2 times the rank times C2 of V minus R minus 1 C1 squared of V. And you call this the discriminant of your vector bundle V. Okay, so let's do this in a couple of examples. So the trivial vector bundle has trivial Chern classes because it's a direct sum of trivial vector bundles. Having trivial Chern classes is a property enjoyed also by another class of vector bundles, which are constructed as follows. So let rho be a representation of the fundamental group of X. Yeah, then I can produce a vector bundle on X as follows. I look at the universal cover of X, say this is a complex manifold, and I consider the action of the fundamental group on the product of the universal cover with C to the R, where R is the same R into which my representation goes, by the following formula. It's the diagonal action on this product, namely I act with the deck transformation on the geometric factor, and then I act with the representation on the C to the R. Yeah, and then I have an action on this product. It's proper and discontinuous and free, and I take the quotient, and this quotient actually is a vector bundle over the quotient of X tilde by pi 1 of X, which is X, and this is a so-called flat vector bundle on X. Yeah, and for these vector bundles, you can show that the Chern classes are also 0. Yeah. Why do I tell you about this? This is because of the following remarkable result, which links this to semi-stability, and this is called the Bogomolov-Giesecker inequality. Yeah, and let me just give you maybe the earliest version and the one with the most regularity assumptions. So let X be a smooth projective surface and H ample on S. If F is H semi-stable, then the discriminant, so since it's a surface, it's an element in H4, it's just a number, this discriminant is always bigger than or equal to 0. Yeah, that's a topological restriction given by these Chern classes enjoyed by a semi-stable vector bundle. And now there is a very important second part. So if F is, say, locally free, I should have said this here. So in my theorem here, F should be locally free. If equality holds, then the endomorphism bundle of this F is of the form that I just explained. It's flat. So if I have a semi-stable vector bundle, there's a certain equality, and in the extremal case, some associated sheaf, namely the endomorphism sheaf, is actually flat. Yeah? And just to remark this, so there is an algebraic proof of the first part of this theorem. It's non-trivial, but it's maybe nowadays standard. The second part is somehow very hard. It uses analysis for the case that the bundle in question is a direct sum of stable with the same slope, so polystable. And then you have, in order to go from polystable to semi-stable, you use ideas of Simpson on differential graded categories. Yeah? And so I want to finish this lecture with 2 examples, namely showing that without semi-stability, these 2 conditions, or this condition on the discriminant, is not enough to guarantee flatness. Yeah? And the first example is somehow sheaf theoretic and very basic. So you look at G, which is a direct sum of O minus 1 and O of 1, then, okay, since minus 1 is not 1, this is not semi-stable, but the first Chern class, which is the sum of minus 1 and 1, is 0. And since you're on P1, the second Chern class is trivially 0. Okay, now you take P1 times P1, product of P1 with itself, and you project to one of the factors, and then you pull back G and you call it F. This is not semi-stable with respect to the natural polarization, but the first Chern class and the second Chern class, by these pullback properties of the Chern classes, they are both zero. However, the fundamental group of your P1 times P1 is trivial, so this F is clearly not flat, because otherwise it would be the trivial bundle. Okay, and then the last example leads me to the topic of the second lecture. It's a geometric example which is constructed as follows. You looked at weighted projective space. This is so C4 minus 0 modulo C star acting with weights 1, 1, 1, and 3. It has only one isolated singularity of the form C3 mod Z3. And then you take some hyperplane section in some embedding, and then you compute, and you, so that's a surface X, see down here, you compute that the discriminant is 0, but I claim that the endomorphism of this sheaf is certainly not flat. And in order to understand that, I have to explain the things I explained in the second lecture. So I will stop here and thank you for your attention. Thanks.
Thank you.
Thank you. Okay, any questions?
This Bogomolov inequality is the same as Miyoko-Yau for surfaces, or is it quicker? I always forget.
No, so actually, so you point out something which will appear in my third lecture.
Okay.
So okay, let me share again. Let me see. So the secret is in the sort of the coefficients here. Yeah. So you see here you have 2r and you have r minus 1. Whereas if you look at Henri's lectures, this is, you will see on a dimension, on a surface, the Miyao-Kayao will have, so it's 2r plus 1 and you have r here. So there is a shift by 1.
Okay.
So, and so it's not just, so Miyao-Kayao is not just Bogomolov for the tangent bundle.
All right, so it's strong. Yeah.
It's stronger, and the question is, what is the correct rank 3 bundle that you should look at?
Okay, but let's not hurry, right?
No.
Yeah.
I also have one question. So at some point you mentioned this theorem of Flanner about if you vector bundle is stable, then the generic restriction is stable. My question is, do we have in some sense a converse of this statement?
Yes, so that's almost by definition, yeah, because you can compute these. So I mean, okay, let me see. This is true. So I mean, if you want to compute these intersection numbers, in the end, they are computed on a curve. Yeah. So the slope is C1 times h to the n minus 1 over the rank. And if you have a vector bundle, if you have a sheaf which has a subsheaf which violates that, for example, on a surface, on a hyperplane, then it will violate. Yeah. Yeah. Okay. Okay. Maybe that's not the right. The question. Okay. See. I mean, the answer is yes. And so there is a. It's an if and only if.
Okay. Thank you.
More questions? Okay, if not, let's thank Daniel again.
Thanks.
And we have like 8-minute break.
Okay.
And we're back.